So in this video, we'll take a look at the different types of waves. There are 3 types of waves, and we'll really focus on 2 of them. I'll give you a brief description of the 3rd wave, but it won't be required for the purposes of this course. So the first type of wave, and let me just say the different types of waves are based on the way that the medium moves compared to the way that the wave velocity or the wave propagation travels. So in the transverse wave, the comparison between those two is that the direction of propagation or the direction of the wave velocity is going to be perpendicular to the direction that the disturbance or the displacement. So that is to say that the medium will move in one direction, the disturbance or the displacement will be in one direction, and then the direction of the velocity of the wave will be perpendicular to that direction. And the best way to explain that is to draw an example. So I'm going to draw, first of all, the equilibrium position. So here's the equilibrium position. And let's imagine that, for example, that we have a string. So a wave on a string, or light, is also another great example of a transverse wave. Definitely want to memorize that light is one of the great examples of a transverse wave. But I think to visualize it, it'll be easier if we think about the string. So this would be the equilibrium position of the string. And what I'm going to do is I'm going to take the string, I'm going to go back and forth like this. And as I go back and forth like this, I'll see a series of waves that are being produced on the string. And so those waves might look something like this. Doing my best to make these symmetric, but might not be perfect, but close enough. So I have basically taken the string and I've gone back and forth like this, and as I did that, the disturbances began to move down as they transmitted their force to the part of the medium next to them. Then that caused that portion of the medium to start moving, and so now all the parts of the string are oscillating back and forth. So really important to notice that if I picked a particular spot on the string, let me pick this spot right here at the top of this hill. So if I pick that spot and I put a little marker on the string, so let's say I put a little marker on the string right here, this is what I would see the string doing. I would see that little marker on the string go up, and I'd see the little marker on the string go down, and I'd see it go back up, and it would just go back and forth between there. So this is the direction of the motion of the medium. The medium is moving up, and the medium moves down. Okay, so the medium only goes up and down, but the direction of the wave is traveling to the right. So this hill right here, I'm going to see this. If I watch over time, I'll see this hill slowly moving to the right, or possibly quickly moving to the right. The hill will be migrating to the right as the force that this guy has created is exerted on the medium to its right. So the direction of the velocity, or the direction of the wave's propagation, is to the right. So up and down for the direction of the medium, that's the disturbance or the displacement, and the direction of the propagation of the velocity is to the right. So those two guys are at right angles to each other. Now there's other aspects of the wave that we can see when we look at this diagram of the wave. So one thing that we've talked about was simple harmonic motion, and remember, this guy is a simple harmonic oscillator. He is going back and forth following simple harmonic motion, is that his maximum displacement, the place where he is displaced furthest from equilibrium, is called the amplitude, and we use the symbol A to represent that. But there's another thing that I can see in here, and that is something which is a new property that we did not talk about with simple harmonic motion. That is something called the wavelength, and that is just simply how long one wave is. So that is the distance from one point on the wave to the next consecutive repeating point. Very important that you put that word consecutive in there. The wavelength is the length of one wave, and the way you would measure that is by going from one point on the wave to the next successive or the next consecutive identical point. So in this case, if I'm at the top of a hill, I want to move along until I get back to the top of another hill. I could go from the bottom down here to bottom, or I could go from, for example, this point, I'm at equilibrium, but I'm rising, and I come over here, I'm back to equilibrium, but I'm not rising, I'm descending, so I'm going to continue going until I finally get to right here. This would be the length of one wave, because at that point now, I begin to repeat myself. So the wave just continues to repeat itself over and over and over again. So two other properties that I can see for the transverse wave is the amplitude and the wavelength. Now for the transverse waves, we give special names for this guy, the lowest point, and special name for this guy, which is the highest point. So as I've been calling this a hill, and another word for the top of a hill is the crest. So the crest is not just like the hill, the crest is the top of the hill, the highest point, where the amplitude is located. And down at the bottom, this guy is called a trough. That's a little bit of an unusual word, but shouldn't be that unusual because there are other words that actually are pronounced in the same way. For example, if I just took the T off, then this word would be pronounced rough. If I got rid of the R, that would be pronounced tough. So that idea of ending O-U-G-H with the kind of an F sound is in several other words that you're very, very familiar with. And now I'm just putting the two together, and so this is called the trough. The trough is the lowest point. So here's another trough, and then here's two crests up on the top, and here's a third crest over here. So it's just a specific label for the highest and the lowest points on the wave. So that is a transverse wave. One last thing I'd like to comment on about the transverse wave is that transverse waves travel in solids only. Because the only way that the transverse wave can be transmitted is that this guy has to be physically connected to the guy next to him. So if there is no physical connection between him and the part of the medium to his right or to his left, then he can't exert any force. So when he begins to get pulled upward, because he's connected to the medium which is to his right, he exerts that force on the guy to the right. If he was not connected to the guy on the right, then he could not exert any force on that. So he could go up and down, and he could execute simple harmonic motion, but there would be no disturbance to travel along the medium. So in a liquid and in a gas, since the molecules are not physically bonded to each other, transverse waves cannot travel through a liquid. That's a really important thing when we look at geology, for example, because we find that transverse waves will not travel through the center of the Earth. And the implication of that is that the center of the Earth must be liquid. There must be a liquid portion of the Earth that is preventing the transverse waves. So transverse waves can travel through much of the Earth, but they can't travel through the middle of the Earth because the Earth's interior in the center turns out to be a liquid. So that's the transverse wave, and our two best examples are waves on a string or light. This might seem like this is also a drawing of water waves, but water waves are technically the third kind of wave that we'll talk about later. You might get away with saying water waves as an example of transverse waves, but if I had to pick one as my example, this would be my go-to example for the transverse wave, I would pick light. Light is going to be your best example of a transverse wave. If you're trying to visualize the transverse wave, I probably use the wave on a string. But you can actually produce more than one kind of wave on a string. I can produce the second type of wave also on a string. So light is probably your best example. But when you visualize it in your mind, you probably want to think about that string. So our second type of wave is called the longitudinal wave, and as you might imagine, it's sort of the opposite of what's happening with the transverse wave. So rather than the direction of the wave's propagation or the direction of the wave's velocity being perpendicular to the motion of the medium, in this case the direction is parallel to the direction of the disturbance or the displacement, or you could also say the direction of the medium's motion. This is a little more difficult to draw. I'm going to do two different drawings of it. First I'm going to use a slinky. So if you can imagine, a slinky is kind of this very weak spring, it's very long. And it can be stretched out, and what I'm going to do is, and you might want to watch me draw, so wait till I get the drawing completed before you try to draw it. So what I'm going to draw is places where the slinky is very scrunched up, it's pushed together, and then, so I drew three little spots, three little rings of the slinky, and then now three portions of the slinky which are very stretched out. And then I'm going to do three again in a row who are very scrunched up, very close together. And then I'll do three more which are very stretched out. I'm going to finish this off with one more scrunched up, one more place where everybody is squeezed together. And then now what I want to draw is, what would the slinky have looked like if it didn't have all these places where it was stretched out or where it was scrunched up? So its normal position would look something like this. somewhere in between. Not as scrunched up as the squeezed together areas, but not as stretched out as the stretched out areas. So this is what it looks like at equilibrium. So the equilibrium position is this spacing, and in some places what I've done is everybody has been moved closer together, and in other places people have been moved further apart. So what ultimately is happening is these squeezed together places and these stretched out places are moving to the right. So everybody is moving to the right as these are the disturbances. Each of these represents a disturbance, a portion of the wave, and they are moving to the right. So they will arrive here, and the first thing will happen to the medium over here is that it will scrunch together. So these guys will push into the guys next to them, and they will cause them to become scrunched together. As they pass through, the next thing to come behind them will be the stretched out area, and then this region over here will become stretched out. So if you can imagine what's going to happen to the medium over here, the medium is first going to, as the compressed area arrives there, it's going to push it to the right, and it's going to squeeze everybody together. Then the stretched out area is going to come by, and that's going to cause everybody to move in the opposite direction. So first they'll move to the right, then the stretched out area will come in there, and they'll start to pull them back to the left. And then the next squeezed area, and that'll push them back to the right. And then the next stretched out area will pull them back to the left. So what's going to happen is the medium, if you can imagine a small spot on the medium, is that the medium is being pushed to the right, and then it's getting pulled back to the left. So unlike the transverse, which was going up and down, this one is moving left to right. If you could look at one little marker on the slinky, you would see it go to the right and to the left, to the right and to the left, to the right and to the left, back and forth, as these successive stretched out and squeezed together areas are passing through it. Now they give names for these guys. The places where they are squeezed together are called compression or compressions. And the places where everybody is really stretched out, those are called rarefactions. So compressions and rarefactions. So here's the key thing about the longitudinal waves. The direction of the wave is to the right. Here's V. And here is the direction of the medium. So the medium is left and right, and the direction of the velocity is to the right. Those two things are parallel to each other, and so this is what defines the longitudinal wave. The medium moves in the same direction, or parallel direction, to the direction of the wave velocity. Now, one thing that's kind of fascinating about the longitudinal waves is that they actually can travel through liquids and gases, and also solids. So essentially the longitudinal waves can travel through anything. So let me draw for you what it might look like, for example, if you were sending a longitudinal wave through air. So as I'm speaking to you right now, it's because I create sound waves in the air, and those sound waves are longitudinal waves. And what they do is they basically squeeze the air together in some places, and in some places they kind of stretch the air out. So let me draw a second picture to show you what that might look like. So what I'm going to draw is going to be air molecules. So these are places where the air molecules have been squeezed together. These would be a compression. And then there's going to be places where the air molecules are very stretched out. And then there will be again a successive. There will be another place where everybody is squeezed together. And then I'll find that there is an area where everybody is very stretched out, followed again by another area where things are squeezed together. And so here is the rarefaction. And if I could just add one more thing to this diagram, just as up here I went from one crest to another, that defined what the wavelength was, that defined what it was to be the length of one wave. I can do the same thing with this guy. So for example, I could go from this location to this location, from one, you could think of these as a crest. So this is the place where, for example, the density of particles is higher than normal. So imagine it's higher. If I'm looking at a graph of density, I would see a peak. The density has increased. And then this guy is a place where the air has been stretched out, so it's at lower density. So I effectively have a crest, a trough, and then another crest. So from crest to crest would be the definition of the wavelength. So the distance between these two squeezed together areas, that would be the definition of the wavelength. So the way that it works is that as this compression moves to the right, what's going to happen is all these molecules are going to run into these guys, and as they run into these guys, they're going to squeeze them together, and in that way, the wave is going to continue to progress. After each compression goes by, everyone will be allowed to relax and to stretch out into the space that's left behind the compression, and so you'll see the molecules move first to the right, and then everyone will relax back to the left, and then they'll move back to the right, and then they'll move back to the left. So the longitudinal wave can travel through solids, liquids, and gases. So we find that when earthquakes occur, the transverse waves do not make it through the center of the earth, but the longitudinal waves do make it through, no problem. Longitudinal waves can travel through liquids, so that liquid outer core of the earth, that doesn't stop the longitudinal waves from making it all the way through the earth to the other side. So just one last thing to just clarify for the longitudinal waves. So when we talk about a compression and a rarefaction, right, a compression is a region where the medium has higher than normal density, and then a rarefaction is a region where the medium has lower than normal density. You could also, if we were talking about a gas or even a liquid, we could also replace the density concept with the idea of pressure. So here where the molecules have been squeezed together into a smaller space, they are under higher pressure, and here where the molecules have been stretched out or rarefied, those particles are under lower pressure. So when you think about the compressions and rarefactions, it could be density, and that's totally valid, as will always be valid. But if we're talking about liquids and gases, pressure is probably equally accurate way of describing what the compressions and rarefactions are, what is actually happening in those regions. The air is being put under higher pressure, or the air is being put under lower pressure than what would be like the normal or the equilibrium area. Now there is a third type of wave called a surface wave. The surface wave is sort of a combination of the transverse and the longitudinal. In the case of the surface wave, what you need to have is actually two mediums. It's not enough to have one medium, to have a string, or to have a slinky, or to have air. You have to have two mediums. So the surface, it should kind of make sense, the surface wave is the boundary between two surfaces. That surface might be air and water, or it might be water and land, or it might be between land and air, but you need to have the boundary between two mediums. And the wave does not travel on either medium, it travels along the boundary between the two mediums. So when you look at water waves are surface waves, because while you don't think about it probably, the shape that you see when you see the waves going like this, that is also occurring with the air. So in places where the water moves up, it pushes the air out of the way, and so the air has that same sort of shape. And in places where the water moves down, the air fills in to fill in that gap. So you see the shape of the waterways, but you might not think about the fact that the air also has the same shape, because there's a boundary between those. So as the water moves up or down, the air has no choice but to go along with it. And that's what a surface wave is. The reason why I say the surface wave is kind of like transverse and longitudinal combined together is that essentially what happens is you get up and down motion and you get left and right at the same time. So if you combine up and down with left and right, what you end up with is kind of a rolling motion. So if you imagined like a duck, for example, sitting on a water wave, you would see that as the water waves passed by, they lift the duck up and they lower the duck down. But as the wave passes by, and you imagine the duck, as the wave is passing by, the duck is on the side of a hill. And when you're on the side of a hill, you start to slide down the hill. So as the duck is on the one side of the wave, it starts to slide down, starts to slide to the right as it's being forced up, and then it starts to slide backwards as it gets on the back side of the hill. Then it starts to slide back to the left. And then the next wave comes by and pushes it to the right and lifts it up. So what you end up with, if you really watch carefully what happens to a duck when it sits on the water and the waves, is it's kind of a rolling motion. And you might have even experienced it yourself. If you go to the beach and you go someplace where there's significant waves like the ocean, you can feel that you're not just going up and down, but there's kind of a back and forth motion at the same time. There's sort of a rolling motion going to it. For the purposes of this course, we really won't talk much about the surface waves. They're very interesting because when there are earthquakes are produced, a lot of the damage is caused by that rolling motion. You can imagine that that's not something that buildings withstand very well. But for the purposes of our course, we will mostly focus on either the transverse or the longitudinal waves. We really won't talk much about the surface waves. If you said that the water waves were transverse waves, you probably would get away with it. They're similar to the transverse waves, but technically the water waves are surface waves. So transverse, perpendicular, the medium and the wave velocity. Longitude, parallel, the motion of the medium and the motion of the wave's velocity.